Welcome to our tutorial on explainability for natural language processing at AACL 2020. We are a group of researchers working on different aspects of AI research, including social science, natural language processing, and human-computer interaction. In the next 3 hours, we are going to talk about the explainability for natural language processing from different aspects. Specifically, this tutorial contains 4 parts. Part 1, Introduction. Part 2, Current state of XAI research for NLP. Part 3, Explainability and case study. Part 4, Open challenges and concluding remarks. So let's get started.
Before we work on solving any problem, the most important question to answer is why we need to work on it. In this part, I will present a high-level overview of why explainability is an important research problem to work on and what are the associated challenges. Since NLP is an important area of AI and the need for explainability is universal for all AI areas, in this part, I will motivate the need for explainability for AI in general, with a combination of examples from NLP as well as other areas of AI. Towards the end of this part, I will discuss specific challenges for explainability for NLP. I hope that I don't have to convince anyone that AI is becoming increasingly important and widely adopted. As you can see from the few news headlines, AI is ready for its prime time and is transforming almost every single industry from retail to banking to government. It is changing the life of everyone in the world. Here is a high-level overview of the simplified life cycle of an AI model. As can be seen, the life cycle of an AI model consists of 6 iterative stages. First, business understanding. In order to decide what model to build, one needs to first understand what is the high-level business problem to solve and what is the technical solution to help solve that problem. For instance, an important high-level business problem for companies like Netflix is how to provide more relevant content to its customer. And one potential technical solution for this problem is to build a better recommendation model for movies and TVs. Second, data acquisition and preparation. Once one understands the technical solution and what kind of models to build, the next step is to acquire the appropriate data and prepare the data accordingly to help the development of the model. The third stage is model development. This is the stage where one actually builds the models. Most of our research focuses on this stage. The fourth stage is model validation. This is a stage where one validates and confirms that models are built as intended. The fifth stage is deployment. This is a stage where the validated model is put for production and used to solve the actual business problem in a larger business process. The final stage is monitor and optimize. Post-deployment, we still need to monitor the use of the model and ensure that it is functioning and used as intended. Additional improvements may be made to further optimize its quality and performance. I will now discuss in more details the needs for explainability in each of the stages. In the research community, when we talk about explainability, most of the time our work focuses on the needs for explainability from an engineering perspective. The engineering perspective mainly involves 2 stages. The first one is model development. During this stage, The model developer, who are often AI engineers or data scientists, often needs to go through the iterative process of feature engineering, including deciding which pre-trained language model to use, model selection and refinement, the actual model training, evaluation, and error analysis. Explainability of a model is important to help the model developers to identify the possible root cause of the errors and improve the model. In our example, during the error analysis, when the model developer found that a particular instance, such as $100 is due at signing, is not classified as an obligation, by inspecting explanation provided by the model, they can find that root cause of this error is that entities such as currency is not considered as a part of the model, and possible ways to improve the model could be adding entity type currency as a feature or introduce entity-aware attention to the model. Another important stage where explainability is required from the engineering perspective is the stage of monitor and optimize. Similar to what we have seen in model development, when by analyzing user feedback, which could be provided explicitly or implicitly, AI engineers identify that clauses related to trademark in contracts are incorrectly classified as IP. Based on this feedback and also explanation provided by the model, one can identify that this error is caused by the out-of-box model, which considers trademark-related clauses are part of the IP category. One possible way to improve the model is to create a customized version that can distinguish trademark-related clause from other IP-related clause. Clearly, from engineering perspective, explainability is important. Now I will explain why it is even more important from the practical perspective. Before I go into the details, let's first take a quick glance of this interview with Regina Basile, a well-known NLP researcher and the first winner of the Square AI Award, on why we are not ready for AI. I will not go through the entire article, but just share a couple key points. During the interview, Regina calls out that it is difficult to adopt AI tools into a process and make sure it's all properly regulated. As a result, as much as she thinks that AI is the technology of the future, unless we figure out a way to trust it, we will not see it moving forward. As Regina has called out, it is critical to establish trust in AI. Many others have conveyed the same message. The needs for trusted AI leads to the needs for explainability. For one to trust AI, there are two basic requirements. First, users of the AI should be able to see with certainty how AI reaches decision. Second, AI need to be brought into the workspace in a careful manner and taking existing business process, practices, regulations into consideration. Now I will revisit the AI lifecycle discussed a few minutes ago and explain in more details why explainability is important from a practical perspective throughout the AI lifecycle. When building a model, the first critical question to answer is to understand whether explainability is needed, and if so, what level is required during different stages in the AI lifecycle. For instance, there are cases where explainability are not needed at all. Such cases in general fall into two categories. The first category of cases are those where there is no significant consequence for unacceptable results. Such cases are fairly common in our daily life. Thinking about movie recommendation, advertisement, and search. You don't really expect the underlying AI model to provide detailed explanation of their results. Since the impact of unacceptable results may not be desired from business point of view, the consequence in general is relatively minor to individual users. The second category of cases are those that have been sufficiently well studied and validated in real applications. Thinking about postcode sorting system and airborne collision avoidance system. For such systems, we in general trust the system's decision, even if it is not perfect. However, in many cases, explainability are not only necessary but mandatory by regulation. Here are just some example regulations in Europe and US that demand different degree of explainability in various aspects of AI life cycle. For instance, US Federal Trade Commission has recently published a guideline on using artificial intelligence and algorithms. Let's highlight a few of the key requirements here. First, if you deny consumers something of value based on automatic decision making, explain why. Second, if you use algorithm to assign risk scores to consumer, you also need to disclose the key factors that affected the score, rank ordered for importance. Third, if you might change the term of a deal based on automated tool, make sure to tell consumer. As you can see, explainability is not just a nice to have feature, but often mandatory by regulations. The need for explainability is mainly related to the quality of data. A specific quality problem of increasing concern is data bias. As we all know, dataset may contain significant bias. But to make it worse, models can further amplify existing bias. For example, in a 2017 EMLP paper, the authors have shown that while the original training data is biased in the sense that only one-third of the agent row in cooking images are men, the trained model performed even worse. It predicts only 16% of the agent row in cooking images are men. As such, it is really important to explicitly capture measures to drive the creation of a better and more inclusive algorithms. There are quite a bit of work in the area in recent years, such as dataset nutrition label and data statement. All this work seeks to do is to capture key aspects of each dataset to make all the different information as transparent as possible. So we already have discussed the need for explainability during model development earlier. Now we will discuss the need for explainability during model validation. Model validation is a core element of model risk management. There are two major goals for model validation. The first goal is to verify that models are performing as intended. The second goal is to ensure that models are used as intended. Defective models can lead to major loss. For instance, in 2012, a computer glitch in the trading software of Knight Capital has costed the company $440 million in just 30 minutes, over $10 million a minute. Even when defective models are found during model validation stage, it may not always be possible to fix them when the models are not explainable. For instance, a couple years back, it was reported that Amazon stopped a secret AI recruiting tool because it shows bias against women. Despite attempts to fix the tool, it was putting off the shelf because there is no way to guarantee that the machine would not derive other ways of sorting candidates that could prove discriminatory, since it's not clear why it was biased against women to begin with. Incorrect use of models can cause just as much harm, if not more. A famous example of misuse of model is London Well. In this case, a trader of JP Morgan was faithfully executing strategy demanded by the bank's risk management model. However, he misjudged the amount of liquidity in the market and used the model in the wrong way. Because the model was inadequately governed and validated, the mistake led to $6.2 billion loss plus additional $920 million in penalties. Not preventing the misuse of model not only can cause major financial loss, such as the case in London Well, it can also cost life. For instance, in recent years, there were multiple instances of the misuse of autopilot feature by Tesla drivers. The National Transportation Safety Board demanded Tesla to do more to prevent the misuse of its autopilot feature. During model development, explainability of the models is often important to ensure they comply to regulatory and legal requirements, as well as build trust with key stakeholders. For instance, Amsterdam government has recently built an algorithm register for all AI models used as part of the city services, such as automated parking control, holiday rental housing fraud risk management, etc. The registry includes both high-level information about each of the models as well as information about the system, including which dataset was used to develop the model, what kind of data processing were involved, what kind of measures were put in place to ensure that the model is fair and unbiased, what kind of human oversight was involved, and finally, what kind of risks were involved. In addition, the city allows the users of the registry to provide feedback on usefulness of the information. Such transparency is widely praised to help foster trust for key stakeholders who are impacted by the deployment of the models. Explainability is important for monitor and optimize stage from the engineering perspective as we discussed earlier. It is also important from the practical perspective. We need to carry out regular checks over real data to ensure the systems are working as intended on an ongoing basis. We also need to establish KPI, stand for Key Performance Indicators, and a quality assurance program to measure the continued effectiveness of the model. Failure to do so can lead to unintended consequences. For instance, some of you may still remember what happened a few years ago when Microsoft released a chatbot called Tai. Within less than 24 hours of its release, Tai learned to post offensive tweets and became increasingly paranoid. If automatic monitoring and quality assurance program is put in place with the right type of model, the bad behavior could potentially be caught early on and corrected before it went out of control. Unfortunately, in the case of Tai, because of its black box nature, it was hard to intervene, let alone to optimize and improve. As a result, it had to be shut down. We also need to carry out regular checks to ensure that systems are used as intended. For instance, it was recently reported that a GPT-3 bot was posting comments on Reddit for a week without anyone noticed. It even provided advices on how to handle suicidal thoughts, and if not done correctly, could lead to real severe consequences. I hope that by now I have convinced some of you that explainability is important from both engineering and practical perspective. Now, I define a few of the important terms to be used throughout the rest of the tutorial. First, black box AI. Today's black box AI models are the main driver for the AI products. When a black box AI model provides decisions or recommendations to a user, it is often difficult to understand why the model produces or does not produce a particular result. It is almost impossible to predict when it will succeed or fail. Correcting a specific errors also tend to be quite challenging. Explainable AI seeks to provide clear and transparent predictions. When it provides decisions to user, it can also provide explanations to help the user to understand why the model produces or does not produce a certain prediction. Such level of understanding can lead to more trust of the system by the users. In the literature, the term interpretability is often used interchangeably with explainability. In this tutorial, we make the following distinction of the two terms. Interpretability refers to the degree to which a human can consistently predict the model's result. The prediction may be made without truly understanding why. Explainability refers to the degree to which a human can understand the course of the model's results. The understanding needs to be based on knowing why. As a result, explainable models are interpretable, but the reverse is not always true. In addition, there is a spectrum of interpretability and explainability. As we will discuss in details in part 2, most work today focuses on provide certain degree but not a full degree of interpretability or explainability. Since this tutorial focuses on explainability for NLP, one question you may have in mind by now is how explainability for NLP is different from explainability from other areas of AI. Here, I will use two simple examples to illustrate the key differences. First, let's look at this example of how one may explain an image classification prediction. As you can see from the picture, for each of the prediction, the top three classes are highlighted by the superpixel with positive weights towards a specific case. Now, let's look at an example of text classification. For each of the labels predicted, attention visualization are used to provide explanation on the prediction. So the question is, which one takes you longer to understand, the left one or the right one? Obviously, the two tasks are the corresponding explanations are quite similar to each other in nature, but do we actually see a difference in terms of difficulty to understand? For most people, the explanation for text classification task takes more time. The reason is the following. Understanding the explanation for the image classification task is mostly a perceptual task that we humans are hardwired to do and hence requires minimal effort. Meanwhile, understanding explanation for the text classification task is a graph comprehension task. Based on psychology literature, graph comprehension generally involves three iterative processes. One, encode the visual array and identify the important visual features. Second, identify the quantitative facts or relation that those features represent. Third, relate those quantitative relations to the graphic variables predicted. Clearly, graph comprehension is a cognitive task that requires significantly more cognitive load than perceptual task. In summary, the text modality associated with NLP tasks does lead to additional challenges in providing explainability. First of all, generate and Display explanation often requires the mapping of information in the text modality to information in visual modality. Some of the challenges are outlined in the survey paper on text visualization if anyone is interested in learning more details. Then, as explained earlier, comprehend the explanation generated for NLP model can also result in higher cognitive load. The last but not the least, as shown in this chart, different stakeholders are involved during different stages of the AI lifecycle. In explainable AI, whether and how explanations should be offered to stakeholders with different level of expertise and interest. In part 2, when we discuss different techniques, you should think about what techniques are suitable for what kind of stakeholder.
In the second part of this tutorial, we are going to dive into the current state of explainable AI research for NLP. The outline of the second part is shown here. We'll start with introducing the methodology we adopted to review papers from NLP conferences. Second, we will talk about the major categorizations of different types of explanation. Third, we'll dive into various techniques that generate and present explanations to the end users. Fourth, we will take a one step back to discuss some other insights we learned from our literature review. In particular, we will use the interactive website we have built for this work to show some of the insights. And finally, we will discuss what are the existing methods for evaluating the quality of explanations and what are the gaps we have identified. We first provide some background information about our literature review. We would like to emphasize that the purpose of this tutorial is not to provide an exhaustive list of XAI papers. Instead, we would like to try our best to find some of the representative works in the past several years. In particular, we focused on major NLP conferences including ACL, EMNLP, NACO, and Calling. We also include some of the representative works from some other general AI conferences such as AAAI, Ichikai, KDD, and etc. We collected and reviewed papers from 2013 to 2019. The way we determine if a paper can be a candidate paper for XAI for NLP is the following. We check if the title of the paper contains the keywords that indicate explainability. For example, explainable, interpretable, transparent, etc., and their lemmatized versions. The way we searched for candidate papers will certainly miss some of the papers that actually works on explainability, but our assumption was that if the title of the paper does not have these keywords, it indicates that the authors of the paper may not think they are working on an explainable AI paper. On the other hand, if the title does have these keywords, then it means that the authors strongly feel that they have an explainable paper. Once we determine the set of candidate papers, two NLP researchers first scan through all the candidate papers to make sure that they are truly about explainability for NLP. Then every survived candidate paper will be reviewed by at least two NLP researchers, who will determine the categorization of the proposed explainable AI work, what are the explainability techniques and the visualization techniques adopted, and whether they have any evaluation. If there is any disagreement, a third reviewer will be asked to review the paper to break the tie. As a result, we found 107 candidate papers passed the first screening using our search criteria, and 52 of them ended up being included in this tutorial. Here we list the top 3 NLP topics of these 52 papers, where we can see that question answering is the most popular NLP topic studied, followed by computational social science, social media, and followed by syntax, tagging, chunking, and parsing. The top three conferences that have the most number of XAI works are EMLP, ACL, and NACO. With all the expandable AI papers we identified, the first task we did was to categorize their explanation strategies into different types. There are many different ways to categorize explanations, and this is where the domain lacks clarity. It's very controversial that if we need a deep taxonomy like the two examples shown here, because this field is still at the early stage and lacks clarity. For example, some of them mixed visualization techniques and explainability techniques. Some of them split the root node based on whether an approach is based on global or local explanation. Some split the root based on whether the model is a transparent model or black box model. People may find that a certain XI work may be placed in different places in the taxonomy and thus cause confusion. This motivates us that we should probably first use a shallow taxonomy and use universally accepted criteria to differentiate different XAI works so that we can build up the standard terminology for this domain and then develop it into deep taxonomy with help from the whole community. Therefore, in our literature review, we look into two fundamental aspects that were widely considered in previous surveys and tutorial. The first aspect is that whether the explanation is for an individual instance or for an entire AI model. Based on this, we have local explanation that focuses on providing justifications for an individual instance, and we have global explanation focusing on revealing the internal mechanism of an AI model. It's worth mentioning that global explanation usually implies local explanation. Local and global explanation are two widely accepted concepts in XAI, not just for NLP, but also for general XAI research. In addition to local and global explanation, we also consider another aspect, which focuses on how these explanations are generated by the XAI approaches. Concretely, is the explanation obtained directly from the prediction process of the AI models, or it requires some sort of post-processing step? With that, we have two categories. First, self-explaining approaches, which means that the AI model that makes the prediction also generates the explanations. And second, post-hoc approaches, which means that the AI model produces the predictions does not generate explanation, and the second post-processing step is required to get the explanation. To give you a concrete example, in the case of local explanation, we can understand only the reasons for a specific decision. That is, only the single prediction or decision is interpretable. A classic example of local explanation is the attention-based machine translation approach, which uses attention to align input-output sentences in two languages and use a saliency heat map to show how the input words and output words are aligned. This is a local explanation method because the saliency heat maps change from instance to instance. It only presents the explanation for a particular decision. For global explanation, we are able to understand the whole logic of a model and follow the entire reasoning leading to all the different possible outcomes. It is easy to see that global explanation implies local explanation. A classic example of global explanation is to use decision tree to predict the outcome of credit card applications. Unlike the salience heat maps shown in previous machine translation task, the decision tree shown here clearly reveals the prediction logic with which we can explain any examples. For self-explaining and post-hoc explanations, the best way to describe the differences between the two is probably using this chart here. Self-explaining approaches have only one model, which produces both predictions and associated explanations. Whereas post-hoc approaches have more than one model, with the first model make predictions and another one or more models to provide explanation. Going back, we can see that the two aspects that we considered here are actually orthogonal to each other, indicating that we can consider different combinations of these aspects. And that led us to draw this simple taxonomy that combines the two orthogonal aspects. The taxonomy we adopted in this tutorial is pretty simple, but should be less controversial, where we first split the root of the taxonomy by global or local explanation, and then for each branch, we check an approach is self-explaining or requires post-hoc processing. Therefore, we have four major categories: local post-hoc, local self-explaining, global post-hoc, and global self-explaining. Although not explicitly shown in the taxonomy, we may derive a preference ranking of this type of explanations. Since we know that global explanation implies local explanation, so global explanation is usually more favorable than local explanation. Additionally, self-explaining approach is probably more favorable than post-hoc approaches, not just because the efficiency issue, but also that self-explaining may have less fidelity issues. We'll discuss this later in this tutorial. I hope that after describing the two fundamental aspects we use to differentiate different XAI approaches, can explain why we consider these four major types of explanations. Then a natural question to ask is, how can we enable these explanations? What are the existing techniques adopted by prior works? And to generate and present these explanations, we are going to dive into this part next. For most of prior work, they took the view that explanations are directly sent from the XAI model to the end user. That is, there's just one step, no intermediate step or fine-grained sub-steps between the XAI models and end user. There's an alternative view, that is, there are actually two sub-steps for explanation to flow from XAI models to end users. Concretely, the first step is the step where the XAI model generates the mathematical justifications for the explanation, and then these mathematical justifications, or we can give them a different name, raw explanations, are visually presented to the end users. In our tutorial, we adopted the second view that is shown here because we think it is beneficial to differentiate the explanation generation step and the explanation presentation step, because the two steps requires different expertise and efforts. Specifically, AI engineers who knows AI better are the right people to work on explanation generation parts, and the UX engineers who knows user better are the right people to work on the explanation presentation part. With this in mind, we next dive into the first step of the whole process, that is the explanation generation step. We will talk about different explainability techniques we observed from our literature review. First, we need to answer the question, what are explainability techniques? We define explainability techniques as the techniques used to generate the raw explanations, that is, the mathematical justifications. As mentioned earlier, ideally, AI engineers are the people who work on this part. From our literature review, we have observed a few representative techniques, including feature importance, surrogate model, example of driven, provenance-based, and the declarative induction approaches. We will discuss each of them in more details shortly. Explainability techniques are high-level strategies that can be used to design the explanation generation process. It is also important to identify a few commonly used operations that can enable explainability. In this tutorial, we will briefly talk about a few of them, such as first derivative saliency, layer-wise relevance propagation, attention, LSTM gating signals, and explainability-aware architecture design. The first explainability techniques we are going to discuss is feature importance. It is the most dominant explainability technique in our literature review. As suggested by its name, the main idea of feature importance is to derive explanation by investigating the importance scores of different features used to output the final prediction. Features are the building blocks from any machine learning approaches, and these features can be manually crafted features, usually adopted by traditional machine learning methods, or they can be latent features learned by more advanced machine learning techniques such as deep learning. Showing the importance scores of these features can provide explanations to the end user how the final decisions are made by the AI models that use these features. From our literature review, we found that manual features, lexical features, and latent features are the main three types of features that people use to derive importance scores for. Majority of the work used deep learning to learn latent features, and they were usually combined with lexical features. For example, learn the hidden states of word or tokens of an input text, learn embeddings of the words and tokens. A few representative works are listed here. We next describe two of them that use feature importance. One of the representative examples of feature importance is the attention mechanism proposed in the work done by Bahadandu et al. In their well-known paper, Neural Machine Translation by Jointly Learn to Align and Translate paper. Prior to this work, encoder-decoder architecture has been used to learn machine translation models, with both encoder and decoder being some RNN type of neural networks such as BioSTM, BiGRU, etc. The main idea is the following. It first uses an encoder to encode an input source sentence by generating a single hidden state that hopefully summarizes the semantic meaning of the whole sentence in a source language. Then the hidden state S becomes the input to a decoder, which sequentially decodes the translated words in the target language. One problem of this approach is that it relies on just the hidden state S and hope it captures the whole meaning of the input sentence, which can be challenging if the input sentence is very long. To resolve this issue, their idea is that we can mimic what humans usually do when we translate sentences between different languages. Concretely, human would first read a whole sentence and then look at the beginning part of the sentence and tries to translate that part first into the target language and then move to the next part of the sentence. Repeat the process until the whole sentence is translated. This motivates the idea that when we generate the translation in the decoder, we can look into every hidden state of the word and token in the input sentence and generate every word and token in the target language by considering a weighted combination of the latent features corresponding to each input word token. The attention mechanism proposed in this approach is a way to learn the weights for the latent features, which naturally becomes the important scores of these latent features for the decoded word and token. Therefore, this is a classic method for enabling feature importance expandability. This is another example of using attention to enable feature importance, where we use attention to enable feature importance for a natural language inference problem. Recall that natural language inference is the task of determining whether a hypothesis is true, false, or undetermined given a premise. For example, here we have a premise saying that children smiling and waving at a camera, and a hypothesis saying that the kids are frowning. We know that this is a contradiction example, and how does deep learning learn the important scores for the lexical features, that is, words in the text in this task? Well, it is done as follows. Words in the premise and the hypothesis are both converted into word embeddings using GloVe pre-trained word embeddings. Then both of them are encoded with the same LSTM, which generates two hidden states, H superscript P and H superscript H, for premises and hypothesis respectively. Then it uses an attention layer to align input-output tokens and use the multiple instance learning to obtain the appropriate threshold values for thresholding attention metrics, which shows the most important input-output token correspondences, leading to the explanation that the most important words are highlighted. The second explainability technique we are going to discuss is surrogate model. As suggested by its name, surrogate models are used as a proxy to generate explanations for predictions made by the original model, usually a black box model. Concretely, given some labeled data, and we can learn an AI model, which could be a black box model or hard to explain model, learned directly from the input label data. Once the training is done, we can use it to make predictions. However, since the model doesn't generate interpretable justifications, that's when we can use a surrogate model, which can possibly use the same set of input examples and the corresponding predictions generated by the black box model to learn a proxy model that is more interpretable. Meanwhile, we also want to make sure that the surrogate model approximates the behavior of the original black box model over a subset of training instances, or all the training instances. Once we have the surrogate model, we can use it to generate explanations to humans. You may have already noticed that one of the nice features of surrogate models is that it is a model agnostic approach that works for any AI models. The most well-known approach that uses a surrogate model is probably the line approach proposed by Ribeiro in their well-known KDD paper in 2017. LIME stands for Local Interpretable Model Agnostic Explanations. As suggested by its name, it generates local explanations. Let's use this chart to illustrate the main idea of LIME. In this chart, the red big cross is the data point that we need to provide explanation. Let's assume that the blue area and the pink area is the ground truth decision boundary for the problem. What LIME does is, based on the data point in question, it samples examples from the training data that are both semantically close and far away from the data point in question to form a subset of labeled data. Additionally, it also gives different weights to these sampled data points according to their distance to the data point in question. Once we have that carefully collected labeled data set, we then learn a surrogate model, for example, a linear classifier as shown as red dashed line in this chart, which is supposed to be interpretable with local fidelity. That is, it correctly identifies the data points included in the newly created datasets. It follows that then we can use the linear model to produce explanation for the data point in question. One of the nice properties of line-based approach is that it is very flexible in terms of the use of explainable surrogate model because it is model agnostic. As shown here in these two examples, you can use different types of interpretable models based on the task you have. You can use models that are suitable for image-based tasks or show the importance scores of different words for a text classification task. Although this is nice, it may raise some concern about the fidelity of the explanations, which we will discuss later in this tutorial. In a line paper, it generates local explanations for a particular instance. Now we show another example, which also uses a surrogate model, but the surrogate model derives global explanation. This work is done by Liu et al. And was published in KDD 2018. The problem that they were trying to resolve is that they wanted to explain a learned network embedding by inducing a taxonomy from it. They first assume that they have a learned network embedding, which encodes nodes in a network into vectors in high-dimensional space, where each dimension does not convey any concrete meaning. What they did is to induce a taxonomy from the learned embedding, which is clearly not an easy task. Their idea is the following. Since they have all the vocabulary of the network and the corresponding embeddings, they divide the embedding vectors into smaller clusters in an iterative manner. The hyperny relation in a hierarchy is modeled by the direct link between a parent cluster and a child cluster. In this way, they distill the implicit relations and patterns concealed in embeddings into explicit organization of knowledge. Here, we only give a high-level description of their work. Interested readers can find more details from their paper. The main differences between Lime and this approach is that this approach starts with all the embedding vectors from the network embeddings and induces a hierarchical structure from all the nodes, thus achieving global explanation. Here are two example taxonomies induced by their algorithm. What they try to show is that within each leaf cluster, the keywords from the documents in the cluster are semantically close to each other. In some clusters, such as M11, it may contain multiple topics, and that is because they didn't continue splitting the cluster. They claim that M11 will be split into two subclusters if they continue splitting it. Example-driven is another commonly used explainability technique. As suggested by its name, example-driven approaches explain the prediction of an input instance by identifying and presenting other instances, possibly from the label data, that are semantically similar to the input instance. The spirit of example-driven approach is quite similar to the idea of nearest neighbors if the examples are drawn from the initial set of training data. We have seen this approach being applied to a few NLP tasks, for example, text classification and question answering. Here is an example that adopts this approach in a text classification problem. More specifically, their problem is to identify what is the topic of a given question. For example, assume that we have a classification model predicting that the question "What's the capital of Germany?" refers to a location. One explanation we can provide is to show another example that we believe is similar to the one we need to explain, such as because we have a similar question in our training data, that is, what's the capital of California, which also refers to a location. And different methods can be used to identify such semantically similar examples. In the work by Croce et al., they used a specific post-hoc mechanism, which is to provide, along with the prediction, a comparison with one or more other training examples that they call landmarks that share task-relevant linguistic properties with the input question. Briefly speaking, the main idea is that they want to identify which training example or which set of training examples are semantically and linguistically similar to the one we need to explain. The way that they identify relevant examples is a method called layer-wise relevance propagation, which was first introduced in computer vision to identify the most relevant pixels in the input data that contributes the most to the final prediction. We will discuss layer-wise relevance propagation later in this tutorial. For now, just think that it is an approach that can propagate the signals that are important to the final prediction from the last layer of the neural net to the input layer. In computer vision, the input layer corresponds to a pixel and an image, and in NLP, the input layer usually corresponds to the input sequence of tokens. The authors of this paper proposed that with some careful design of the neural net, layer-wise relevance propagation can be used for explaining question classification problems. But instead of identifying relevant pixels in question classification, the goal is to identify relevant examples. The idea they had was to extend the layer-wise relevance propagation to a kernel-based deep learning architecture. In a high level, they use kernels to model the similarity between a test instance and the training examples. It follows that the network is triggered by an input vector x expressing the kernel evaluating the similarity between the example and the landmarks or training examples. When using linguistic kernels such as semantic tree kernels, this measure corresponds to the grammatical and lexical semantic similarity between x and the subset of landmarks. The expected explanation is obtained from the network output by applying layer-wise relevance propagation. Again, the technical details of this work can be found in their paper. Here are some examples taken from their paper, which gives you some idea of the kind of explanations they are providing to the user. Some of the examples are quite intuitive. For example, when explaining why the question "what was FDR stock's name" is referring to an entity, the activated examples that they show is a similar question asking "what's the name of David Letterman's stock?" Example-driven approaches are quite intuitive because it uses training data as explanations, which is basically also labeled by humans. The only concern would be if there is a completely out-of-blue question that we don't have any similar examples in the training data. This method may fail to provide any meaningful explanation.
We now turn our attention to provenance-based forms of explainability. In these types of techniques, explanations are provided by illustrating parts of the derivation process for the individual predictions. This is an intuitive and effective explainability technique, especially when the final prediction is the result of a series of reasoning steps. Several question-answering papers adopt this approach. We will take a look at two of them next. Abu Jabal et al. With a system called Quint, and then Zhao et al., which both address knowledge-based question answering, or KBQA. We'll also discuss the third paper by Amin et al., Math QA, in the declarative induction part. since that paper is also a representative example of program induction. We now discuss the Quint system, which provides an interpretable method for question answering over a knowledge base. As an example, here we have a question: where was Martin Luther raised? And the goal is to answer it using DBpedia as the knowledge base. The notable aspect about Quint is that when it answers the question, it also shows the complete derivation sequence. This starts with how it understood the question, which includes solving two tasks, namely entity linking and relation linking. Entity linking is the task of correctly matching and disambiguating each entity mentioned in the question to an actual knowledge-based entity. For our example, Martin Luther in text needs to be matched to the Martin Luther entity in DBpedia and not Martin Luther King Jr., which is a different person. Similarly, relation linking is the task of correctly understanding and disambiguating each relation in the question to a concrete knowledge-based predicate. For example, raised needs to be linked to the DBpedia predicate place of birth, which is associated with the Martin Luther entity. The derivation sequence that then also includes the actual Sparkle query that is formed based on the entity and relation linking steps, and then the final answer, which is Eisleben in this case. As a side note, the Sparkle queries are learned from query templates that are based on structurally similar instances. For example, where was Obama educated is similar to the above Martin Luther question, and the Sparkle query will have a similar pattern in that case. The overall key point about the Quint system and provenance-based systems in general is that the derivation sequence provides insights into what went wrong in the case of errors, and also hints on how to reformulate the question. The next paper addresses the same problem of knowledge-based question answering, or KBQA, but it does so by focusing specifically on more complex types of questions that include multiple relations and entities. This work is deep learning based and develops IRN, an interpretable reasoning network, which breaks down the KBQA problem into multi-hop reasoning steps, where intermediate entities and relations are predicted in each step. As an example, consider the following question: what does John Hammond's kid do for a living? This approach will produce a reasoning path by first linking the entity John Hayes Hammond to an actual knowledge-based entity, followed by two hops of relation prediction. Each row in the figure represents a probability distribution over each relation in these hops. The first row predicts the child predicate, while the second row predicts the profession predicate. Note that the reasoning path can include both named entities and implicit entities. For example, E here in the path stands for the actual child entity, and A represents the answer entity. While this example is a single linear path, the paper also considers more generally conjunctions of such paths. The overall key point of this system is that it facilitates correction by a human, including disambiguating the question. For our example, the question is actually ambiguous since there are three different children, each with their own professions. The user can then have the option to further disambiguate by saying, for example, John Hammond's daughter or second child. We now turn our attention to explanations via declarative induction. The main idea of declarative induction is to construct human-readable representations such as trees, programs, and rules, which can provide local or global explanations. We call this declarative induction because such explanations, trees, rules, programs, often fit into a declarative specification language, which humans can understand and manipulate. Concretely, we will look first at a tree-based paper by Jiang et al., which uses trees to express alternative ways of reasoning in multi-hop reading comprehension. As an example of a program induction, the paper by Amini et al., MathQA, induces specialized math programs to explain math word problems. These two papers represent good examples of local explainability with per instance explanations. Then there are multiple papers that use rules for explainability across a range of tasks, from entity matching to link prediction and sentence classification. One notable aspect about these rule-based papers is that they offer global explainability for the entire model, although the same rules could also be used to produce local explanations. The paper by Zhang et al. Focuses on multi-hop reading comprehension, where the task is to explore and connect multiple sentences or documents in order to answer a question. In this example, the question is to find in which administrative territorial entity is sulfur spring located. Towards this goal, the proposed method locates the relevant documents, starting from the ones where sulfur spring is mentioned, and stitches them into a reasoning tree. This tree plays a dual role. First, it accumulates all the information needed to produce the answer. Each route to leaf path in the tree represents a possible answer and its derivation. For this example, the path from node 0 to node 4 is obtained by following the first document, which contains a reference to Yellowstone National Park, with another document that gives further information about locations of Yellowstone National Park, mentioning Wyoming, Montana, and Idaho. The final answer is aggregated based on multiple evidence across all the route to leaf paths, leading to Wyoming as the correct answer in this case. The second role of the tree is that it can be used to explain the answer and also the alternative choices that were considered during the reasoning. The next paper by Amini et al., MathQA, is focused on using program generation or induction for interpretable math word problem solving. Thus, the task here is to understand and solve math word problems, such as the one shown in this example. The notable aspect of MathQA is that it uses a sequence-to-program translation so that not only it can give the answer to the word problem, but also produce a program with a sequence of math operations that leads to the answer. The program reflects a precise understanding of the textual description of the word problem and makes use of specialized operations and formulas that include the numbers mentioned in the text, but also constants such as the number pi. The method is dependent on how expressive the target mathematical language is. And currently, the system does not handle problems that need complicated or long chains of mathematical reasoning or more powerful languages that may include logic, factorization, or more. We should note that MathQA is also an example that fits under provenance-based explainability, since it provides an answer and how it was derived. Finally, we note that this is a representative example of a system that provides local explainability in the sense of input to output explanations, but gives no global explanations or insights into how the model works. The next few papers will address this. The next system we discuss is Explainer, which is focused on producing explanations for the entity resolution or ER task. This task, also known as entity disambiguation or record linkage or record matching, is a task where given a set of pairs of records, one needs to decide for each pair whether the two records represent the same real-life entity or not. In the example on the slide, we need to decide whether two publications are the same or not. But the same task can be required for other entity types such as companies, people, products, and so on. Explainer is a comprehensive system that offers multiple types of explanations. Given an input model for ER predictions, which is assumed to be a black box model, Explainer can produce local explanations based on the LIME method, which was discussed earlier, and it can also produce representative examples for the behavior of the black box model as well as perform differential analysis with respect to other ER models. From a declarative point of view, Explainer offers global explanations by approximating the overall ER model with an interpretable representation consisting of a Bayesian rule list, or BRL. Such list can also be seen as a tree of probabilistic if-then rules. For the example of the publications, the first rule in this tree says that if the Jacquard similarity of 3 grams applied on author names is less than 0.35, then it's likely that the pair is not a match, or conversely, it is a match with low probability of 30%. Otherwise, we need to go down the tree and apply the next rule, checking additional conditions on titles, which, if true, lead to a prediction of a match with probability 99%. If not, then we need to go check another rule, and so on. As you can see, this gives a pretty good explanation of how the model behaves globally for any input pair of records. We now turn our attention to a paper that uses declarative induction for interpretable link prediction in a knowledge graph. Here we assume that first that there is already an underlying model for link prediction. The proposed method then uses adversarial modifications, such as removal of a fact in a graph, in order to identify those knowledge graph nodes or facts that are most likely to influence the prediction of a link. For example, this type of analysis can find out that the removal of a is connected to link between two concrete nodes, C and B, will have the consequence that when the underlying model is retrained, then the is-connected link between nodes A and B is no longer predicted. Furthermore, instead of focusing on individual predictions, the method aggregates the explanations over the whole dataset for each relation into a set of rules which intuitively correspond to most frequent such patterns where the removal of fact leads to changing the prediction of a link. The rules that are generated are Horn clauses of length 2. In other words, these are implications where the left-hand side is a conjunction of two predicates and the right-hand side is a single predicate corresponding to the link being predicted. The predicate in red in these examples is the one that, when removed, will most likely change the prediction. One notable aspect of this method is that it can work on top of existing black box models for link prediction. In their paper, they used two such prior models, Dist-Malt and Convy, and they derive rules that explain behavior that is in either of the models or in both. As the authors point out, one advantage of having global explainability in the form of rules is that one can pinpoint common mistakes in the underlying model. For example, by looking at this rule for is located in, one can see a pattern for wrong inference in the underlying Convy model. Concretely, the rule says that if A is located in C and C has neighbor B, then A is located in B. But this is wrong. We have seen in the previous approach for rule induction a case where the result is a set of logical rules, more precisely Horn rules of length 2, that are built on existing predicates from the underlying knowledge graph, which could be something like Iago or DBpedia. But there are other approaches that also learn logical rules, but they are based on different vocabularies. We will see next an approach where logical rules for sentence classification are built on top of linguistic NLP-based predicates. Later on, we shall see system ER, which induces rules for entity resolution that are built on different types of predicates, focused on similarity features. So let's discuss now the induction of linguistic rules for sentence classification. The task here is to classify sentences from a concrete domain, such as legal or contracts domain, according to a set of classes. As an example, this sentence talking about notices that will be transmitted electronically in certain ways, should be labeled as a communication sentence. Other possible classes in the contracts domain may be terms and termination, liability, and so on. This is a representative example of a neurosymbolic system that combines neural learning with rules. Concretely, it uses a neural model to learn another model, namely the rules, which are then used for the actual classification of sentences and also to provide global explainability. The rules themselves are built based on predicates that are based on, in turn, on features coming as a result of syntactic and semantic parsing on the input sentence. Furthermore, the rules can make use of domain-specific dictionaries. In this example, the rule states that there must be a verb in the input sentence whose theme must match one of the terms in the dictionary, namely communication or notice. And furthermore, the voice of the verb is passive and the tense is future. If this rule is true, then the sentence can be labeled as communication. One notable aspect of this system is that the deep learning component jointly learns both the rules and the contents of the dictionaries. Another important aspect, as the authors also point out, is that the rules generalize or transfer better to unseen data. Furthermore, they are more conducive for interaction with the human expert and lead to robust human-in-the-loop systems. We will revisit this in the later part dedicated to visualization.
We have discussed the different explainability techniques. A natural question is that what are the operations we may use to enable this explainability? We next briefly talk about a few commonly used operations that we have observed from our other paper we have reviewed, including first derivative saliency, layer-wise relevance propagation, input perturbation, attention, LSTM gating signal, and explainability-aware architecture design. First one we are going to talk about is an operation called first derivative saliency. We observed that it is mainly used to enable feature importance. First derivative saliency was introduced as a neural network visualization approach proposed for computer vision tasks. The basic idea is to compute the impact of each input unit, namely each pixel, to the final decision of the classifier. Let's think of a simple neural net as shown here, with E being the input layer. After going through multiple hidden layers, it finally makes a prediction S sub y of E. Since the neural network basically forms a computation graph from input to the output prediction, once we have the final prediction, usually is a vector of real values, we can compute the gradients of each node in the computation graph, all the way back to the input layer. Intuitively, greater gradients indicate greater impact. Therefore, we can use the gradients of the first layer as the saliency importance score, and that is why it is called first derivative saliency. Since first derivative saliency are importance scores of the first input layer, we can naturally use saliency heatmap as shown here to visualize the importance of the input elements. Here we have a chart taken from the work done by Lee et al., where they were using first derivative saliency to show the importance of the input words to the final sentiment label using different neural network architectures. From this chart, we can also see that comparing to simple RNN and one-directional LSTM, BioSTM provides more intuitive visualization, clearly indicating that the word hate is the most influential word from the input sentence. The next operation is layer-wise relevance propagation, which is quite similar to first derivative saliency that we mentioned earlier. As we discussed in the explainability technique section, It was first proposed for explaining computer vision predictions by highlighting the most evident part of an image. Recently, we have seen quite a few works that extend this idea to solve NLP problems. Similar to first derivative saliency, the idea is to measure the contribution of the input elements to the final prediction. In NLP, that usually leads to characters, tokens, and words. The main difference between first derivative saliency and layer-wise relevance propagation is described by this formula. Here, f of x corresponds to the prediction score or the final output score of a model. Layer-wise relevance propagation distributes this score and assign them to each dimension of the input layer, such that the relevance scores of the input layer roughly sum up to the final score. In particular, if the relevance score at a certain dimension is greater than 0, it means that this feature in favor the prediction. Otherwise, it is against the prediction. Unlike first the derivative saliency that uses gradients as a proxy of the relevance score, layer-wise relevance propagation uses local propagation rules to distribute and propagate the relevance scores from later layers to earlier layers in a neural net, making sure that the relevance score of the input layer can roughly sum up to the final score. For more mathematical justification of these rules, you can find the work done by Montalvan et al. Next, we talk about input perturbation. This is actually one of the most popular operations we have observed. It is usually used to enable local explanation for a particular instance. We saw a lot of surrogate model approaches adopted this operation. Usually, it has a classifier f that is not explainable, and it made a prediction over a particular instance x, denoted by f of x. Since f is not explainable, we don't have any explanation for f of x. Then, based on the input instance x, we use input perturbation to generate a set of m new instances, then use the unexplainable classifier f to make predictions over these perturbed examples. After that, we learn a surrogate model G, usually an explainable model, from the set of labeled examples we obtained through input perturbation. The goal is that we would like to make sure that G well approximates the behavior of f by generating the same labels for the same input instances. Once we have G ready, we can use it to generate explanation for the input instance x. We observe that there are in general two different ways to perturb examples, including sampling-based approach and perturbating intermediate vector representation. Sampling-based approach directly uses examples within label data to get their perturbations, and the second method is specific to neural networks, where it introduces minor perturbations to the vector representation of input instances. We'll next provide more details for each of the two types. The most representative work for sampling-based approach is the Lime paper, which we have discussed previously. Just a quick reminder that Lime is a sampling-based approach because it selects examples from the training data. It doesn't generate new examples. An alternative way to add minor perturbations to input instances is by adding perturbations to intermediate vector representations. Here we talk about a work done by Alvarez-Melis and Giacola et al., where they proposed a method that explains predictions of any black box structure input structure output model around a specific input output pair. So it's local explanation. An explanation produced by their framework consists of groups of input output tokens that are causally related. The dependencies between input tokens and output tokens are inferred by querying the black box model with perturbated inputs. This is a figure taken from their paper that illustrates their approach. The core idea is quite similar to LIME. Basically, when they have to explain an input-output pair, they first obtain perturbated versions that are semantically similar to the original one, but with minor changes. However, unlike getting perturbated version for images, which is simple, getting perturbated versions for sentences is much more challenging. In their work, they used a variational autoencoder, and their goal is to introduce the perturbation in the continuous latent representation rather than directly on the structured inputs. Although it is out of the scope of this tutorial, we would like to briefly talk about how we can use a variational autoencoder to generate variations. The main differences between autoencoder and a variational autoencoder is that autoencoder uses the bottleneck architecture to compress an input data point to a data point in the latent feature space, whereas variational autoencoder defines a probability distribution in the latent space for input data points. Since we have a distribution in the latent space, we can sample different data points from this distribution to get perturbated versions of the input data point. Again, this is a very high-level description, and this topic is out of scope. Interested reader can dive deeper into their paper to get more details. Next one is attention, which is of course one of the most popular deep learning mechanisms. Since we have talked about it before, we will not repeat it again, but just one comment here. We have seen a lot of attention-based operations that enables feature importance explainability in our literature review, suggesting that attention is probably a good starting point for enabling feature importance. Next, we have LSTM gating signals. Clearly, this is an operation that is specific to LSTM-based approaches. The intuition behind this method is that we know LSTM is a classic neural net for sequence modeling. It processes a sequence of input elements at different time steps, and each LSTM cell has different gates, including input gate, output gate, and a forget gate. These LSTM gating signals can determine the flow of information, that is, how LSTM reads the word sequences and how the information from different parts is captured and combined. Once the whole sequence has been processed, we can then look into the gating signals, which are computed as partial derivatives of the score of the final decision with respect to each gating signal. In the work done by Gani et al., when computing the gating signals, instead of considering individual dimensions of the gating signals, they aggregate them to consider their norm, both for signal and for its saliency. After that is done, they visualize the normalized signal of each gate at different time steps, as shown here. The scores is a way to indicate the importance of the elements to the final prediction. Unfortunately, there was not enough details about the formula they used to compute the norm, and it seems that they probably first stabilized the signals so that when computing the norms, the values are within the range 0 to 1. Details please find in their paper.
We now take a look at a few examples of explainability-aware architectural designs that can be used to enable explainability. These are self-explainable or directly interpretable systems, as opposed to ones that require post-hoc explainability. We start by revisiting the earlier paper that uses rule induction for the task of link prediction in knowledge graphs. As we recall from the earlier slide, this approach works on top of existing black box models for link prediction that are based on embedding the nodes and relationships in a multidimensional vector space. A key part in this architecture is the decoder that allows to go back from embeddings back to nodes and relationships on which the explainable part takes place. More concretely, given a target fact such as was born in S and O, where S is the subject node and O is the object node, and was born in is the relationship, denoted in the figure as R, the first step is to embed S and R into the multidimensional space according to the particular black box model for link prediction. Then we find the most influential node that, when removed, would then change the prediction of the target fact. This is solved as a continuous optimization problem in the embedding space. The next step is then to decode the resulting vector, Z S prime R prime, back into actual knowledge graph nodes and facts. For example, we would get is located in S prime and O. Note that the object O is always the same in this case. Since we are, in this method, we are looking for formulas of the form R1 of AC and R2 of CB implies R of A and B, where the same object B appears in both R2 and the target fact R. Once the most influential nodes are detected, a separate step is performed to extract horn rules of length 2 that corresponds to frequent patterns. As the paper states, this step finds simple patterns on subgraphs that surround the target triple and the removed fact, which appear more than 90% of the time. For this example, this may produce a rule such as the one shown here. If A is affiliated to C and C is located in B, then A was born in B. It doesn't mean that the rule is necessarily correct, but rather that it reflects or explains predictions made by the underlying model. Let's now move to our second example of explainability-aware system, which also performs rule induction but uses a very different design based on active learning. This is System ER, a human-in-the-loop system for explainable entity resolution. As we recall, entity resolution is the task where, given a set of pairs of records, one needs to decide for each pair whether the two records represent the same real-life entity or not. Here we are showing a case of entity resolution on entities that are companies. System ER iteratively learns an ER model via active learning from few labels. During this learning, rules actually play a dual role. First, they are used as an explainable representation for the intermediate states, as well as for the final model, once learning is done. Second, rules are also used as a mechanism to generate and explain the examples that are brought back for human labeling. At a high level, the system works as follows. In a given iteration, and given the examples that have been labeled so far by the human, the system learns a candidate rule. For instance, it may produce a rule that checks that corporation name matches company name and that city name are the same. This rule may not be a perfect rule, but it can then be used to retrieve new examples for the human to label. As a result of the new labels, the model is then refined in the next iteration to a better rule, more precise in this case, which checks that additionally the zip codes of the company records must also match. We describe next the exact strategy for example selection. There are two types of examples that are selected during active learning in System ER. The first corresponds to the so-called likely false positives. Given a candidate rule R1, in order to refine R1 so that it becomes high precision, we need to find examples that satisfy the rule R1 but are likely to be false positives. Pictorially, we need to look among the matches produced by R1 and identify candidates for negative examples. This is done by using various heuristics, such as a low number of similarity features that are true on those examples. Once labeled by the human and confirmed as negative, These examples will then contribute back as new training data to learn more precise rules in the next iterations. The second type of examples corresponds to the so-called likely false negatives. Given the same candidate rule R1, the system now explores beyond R1 to find what it misses. More concretely, we now look in the Cartesian product space for possible pairs of records that are likely to be positive matches, but are outside of the current rule. Exploration is done in an efficient way by exploiting a heuristic that drops various predicates from the current rule R1 to construct relaxations of R1, also called rule minus rules. The new positive examples that are found and labeled from these various parts of the search space may then lead to additional rules in the next iterations, thus enhancing recall. A key aspect of this system is that at each step, examples can be explained and visualized based on the predicates that they satisfy or not satisfy. Thus, the human gets an explanation of how the active learning progresses and what similarity features are being used.
We now move to the second part, that is, techniques used for visually presenting raw explanations to end users. The main goal of visualization is to present the generated raw explanation in an appropriate way to end users. Unlike explainability techniques, which are better handled by AI engineers, visualization is better done by UX and UI engineers who know users better. From our literature review, we have identified a few representative visualization techniques, including saliency, raw declarative representations, natural language explanation, and the raw examples. We will talk about them next. Based on our literature review, saliency is the most popular visualization technique. In fact, it is probably the most widely used visualization technique in all AI domains. By definition, saliency is used to visualize the important scores of different types of elements in XAI learning systems. Saliency is very popular because it presents visually perceptive explanations that can be easily understood by different types of users. Here we show an example of using saliency to highlight the most important parts of an image for a computer vision task. Clearly, for computer vision tasks, saliency-based visualization is self-explaining and human comprehensible. Here are two other examples of saliency-based visualization. Both of the charts are visualizations for machine translation tasks. Saliency is used here to visualize the input-output alignment. In particular, the intensity of the color of the cells indicate the input-output relevance score, that is, the saliency scores. It can be seen that saliency heat maps shown here can be understood by humans. We have more examples of the usage of saliency-based visualization. Here are four examples that are not input-output alignment. The commonality among these examples is that they use saliency highlighting to indicate the importance of tokens or words for the final decision that made for their NLP problems. As we can see from the charts, saliency-based visualization is quite flexible in the sense that you may use different colors with different intensities to indicate the impact of words. For example, the chart at the top right corner uses two different highlighting colors, where blue indicates possible impact while pink indicates negative impact. We also see that for positive impact, we can further use different intensities to indicate the significance of different positively impact words. And this kind of subtlety can be easily captured by human.
We now discuss the case of visualization when explanations are given as declarative representations. Recall from the earlier part that the main idea of declarative induction is to construct human-readable representations such as trees, programs, and rules, which can provide local or global explanations. In the case of trees, let's revisit the paper that we discussed earlier on multi-hop reading comprehension. So here, different paths in the tree explain the possible reasoning paths that lead to the answer. One can use this as the basis for visualization, where a user can see the alternative choices of going from the subject of the question to the possible answers, and also can see the final answers that the system arrived at. As opposed to trees, rules and programs are more formal representations or justifications of the underlying models. The logical forms of the rules themselves can give a human expert enough intuition and confidence that the model is working properly. As an example, for link prediction, rules give a formal and concise representation of what causes the various types of links to be predicted. Of course, these explanations also require a certain level of expertise and knowledge from the human. So to further facilitate the understanding of rules by a human, one can then build more advanced systems that use the rules as a building block for visualization of explanations. As a concrete example, the system developed by Sen et al., which we discussed earlier, and learns linguistic rules for sentence classification, also provides an advanced interface for human-machine co-creation of the final model. So this allows not only the visualization of the explanations provided by the machine, but also allows the human to give feedback and customize the model itself. So let's take a closer look at this system next. This human-machine interface, also called HIDLE and described in an HCL demo paper, is a way to visualize, rank, and understand the various rules according to what they do, the predicates they include, and also the various performance metrics that one is typically interested. For example, here we see rules that will predict the label communication for a given sentence. For each rule, we see which predicates or dictionaries they use, as well as performance metrics such as precision, recall, and F1 score. Furthermore, for each rule, the system can drill down into concrete examples of sentences that illustrate the effect of the rule. For instance, one can see examples of relevant sentences that will cause the rule to fire and thus label the sentence as communication. And we can also see examples of sentences that are not relevant to the rule. Finally, the playground mode allows the human expert to add or drop predicates within a rule and see the immediate effects of that. For this particular rule, if the user drops the future tense predicate, the tool indicates that the precision will continue to stay at 100%, while recall will increase from 17% to almost 33%, with a significant increase in F1 score too. Furthermore, the tool displays examples of new sentences in the ground truth that are now covered by the modified rule. Thus, the system allows humans to instill their expertise and domain knowledge on top of the rules that were automatically produced by the algorithm. So in this example, a human expert knows that the future tense may not be necessary, and the tool provides the evidence that this is indeed the case. Overall, as a result of this human-machine co-creation, we obtain models that generalize better to unseen data.
Presenting raw examples is another widely used visualization technique to deliver explanations. Suggested by its name, this approach explains a decision made by an AI model by presenting one or some examples, either from the existing training data or generate some new ones that are semantically similar to the instance needs to be explained. Here is an example that we took from the work done by Pachenko et al. The NLP task they studied was word sense disambiguation. In this particular example, we need to explain the word sense of jaguar in the sentence. Jaguar is a large spotted predator of tropical America similar to the leopard. The work provides multiple explanations, and one of them is example-driven based approach, where they identify two examples that are similar to the one in question. For example, one of the raw example presented is the sentence, "The jaguar, a compact and well-muscled animal, is the largest cat in the New World," which is similar to the one we need to explain. Here is another example. Again, the way this approach used to explain the theme of a phrase in a sentence is by presenting one or more examples, which either can be a positive example or a negative example, or both. The next visualization technique is natural language explanation, which by its name means that explanations are verbalized in human comprehensible language. We found a few work that adopted this visualization technique, and they can be categorized into two main types. The first type is using deep generative approaches to generate natural language explanations, and the second type is to use template-based approach. The first example we show here is the one done by Rajini et al., where they try to explain common sense question answering problems. For example, the question could be, they were getting ready for a really long hike. He put the food in his what? Along with this question, there are a few possible answers, including recycling center, house, and backpack. The QA system may predict that the answer is backpack, and now we need to explain why the system come up with this answer. The proposed method trains a deep generative model to produce the explanations. Concretely, they first ask human annotators to provide natural language explanations for common sense question answers from a dataset with ground truth. So they have the gold answers. What they want from the human annotators is the explanation to these answers. In this way, they can get a training dataset from which they can train a language model from a question with answers and explanations. Once the model is trained, it can be used to generate explanations for future unseen questions. From the example shown here, we can see that for the question we discussed earlier, the human annotator provided an explanation that backpacks are used on hikes, while their model generates an explanation that is not similar to the human annotators, but also quite intuitive. It figures out that a backpack is a place to store food and supplies. The next example we are going to talk about was actually appeared earlier in raw example visualization technique. We think this also falls into the natural language explanation category. Note that the raw explanations are the sentences with underlines. Clearly, there are some transition phrases that connect the raw examples. So the authors of this work made a minor extension to the raw example-based approach, where they used a simple template-based approach to turn raw examples into natural language explanation. Although this is a very simple approach, it actually makes the explanation more user-friendly. Same idea can be applied to some of the declarative representation methods, where we can, for example, turn first-order logic rules into natural language explanation using some predefined templates. Again, this is a minor extension, but it is more user-friendly because not everyone is comfortable with reading first-order logic rules. Now we have talked about different techniques for explanation generation and presentation. We next take a step back from the low-level technical details and look at the big picture. First, we would like to let you know that we have built an interactive website which can be viewed as a living survey or tutorial for XAI research for NLP. Many of the insights we are going to discuss next were directly taken from the website. It has multiple interactive views that provide different ways for the user to explore this field. The link to the website is provided here, and we encourage interested readers to visit the website to explore the field in their own ways. Here is a screenshot of the tree view from our XNLP website, which shows the distributions of the papers we included in our literature review. Recall that when we introduced the four major categorizations, we mentioned that we can actually have a preference ranking for these four categories. That is, global explanation is better than local explanation because global explanation implies local explanation. Self-explaining is also better than post-hoc explaining because there might be some fidelity issue of post-hoc approaches. Therefore, we would expect there have been more effort on global post-hoc and global self-explaining approaches. However, from this screenshot, we can see that global explanation approaches are far less popular than local explanation. In our view, it conveys the message that achieving global explanation is more difficult than local explanation, which in turn indicates that studying techniques that allow us to enable global explanation is one of the future research direction for this field. Same observation can also be identified in list view of our website. Also in this view, users can further sort the papers in each category by their explainability techniques, visualization techniques, venue, and NLP tasks. Our website also provides a cluster view page where the readers can use this interactive chart to identify the distributions of different combinations of visualization techniques and explainability techniques. From this screenshot, we can clearly see that about 30 papers, which is about 60% of the papers that we have included, used the combination of feature importance and saliency as their explainability and visualization techniques. Also, we can see that all global self-explaining methods that are all the black dots in this chart use the combination of declarative representation induction and the raw declarative representation as their explainability and visualization techniques, which partly explains why there are so few global self-explaining methods, because most of the paper we included are using deep learning based approaches and derive declarative representations from deep neural net is extremely difficult, and this is also one of the hot topics in AI right now. Citation graph view is another web page we included in our XNLP website. It shows the evolution of citation network in the past few years. Note that we only visualize the citations among the 52 papers that we included in this tutorial. This short animation can clearly show the evolution of the field and also help us identify some of the most influential work in this field. For example, the paper that introduces Lyme is obviously the most influential work in the past few years. It got a lot of citations from papers that are both focused on local explanation as well as global explanations. The last view we want to mention is the search view of our website. As the screenshots shows here, the search view provides readers the flexibility to perform advanced searches. The user can either use fast search to do more structured searching or use keyword search to search against the metadata of each paper. The static screenshots we shown here don't show all the features of the website. For example, in each view, every paper is clickable, which will show a dialog of this paper containing different useful information, such as representative screenshots from the paper and link to the paper, and etc. In interest of time, we won't showcase all the different ways that the user can explore with the field using our website, but we do encourage interested readers to explore our website to find out other advanced ways to explore the field. Before we close the second part of the tutorial, we would like to talk about how to evaluate the quality of generated explanation. In addition to traditional performance evaluation for AI problems such as accuracy, precision, and recall, an important evaluation we need for XAI approaches is the evaluation of the effectiveness of generated explanations. Given the young age of this field, it is not surprising that there's little agreement on how explanations should be evaluated. From the 52 papers we reviewed, 32 of them didn't have any evaluation or used a very informal evaluation. For example, they only have very high-level discussion of how examples of generated explanations align with human intuition. Some of them even use F1 scores as a proxy to show the effectiveness of their explanations. Very few of these papers adopted some forms of formal evaluation, which can basically be grouped into two categories. One, evaluating with human ground truth data, and two, human evaluations. Several works compare generated explanations to ground truth data in order to quantify the performance of explainability techniques. Employed metrics vary based on task and explainability technique, but commonly encountered metrics include precision recall, F1 scores, and blue scores. While having a quantitative way to measure explainability is a promising direction, care should be taken during ground truth acquisition to ensure its quality and account for cases where there might be alternative valid explanations. Approaches employed to address this issue involve having multiple annotators and reporting inter-annotator agreement or mean human performance, as well as evaluating the explanations at different granularities, for example, token-wise versus phrase-wise, to account for disagreement on the precise value of the ground truth. A more direct way to assess the explanation quality is to ask humans to evaluate the effectiveness of the generated explanations. This approach has the advantage of avoiding the assumption that there's only one good explanation that could serve as ground truth, as well as sidestepping the need to measure similarity of explanations. Here as well, it is important to have multiple annotators report inter-annotator agreement and correctly deal with subjectivity and the variance in the responses. The approaches found in this tutorial vary in several dimensions, including the number of humans involved, ranging from 1 human users to 25 human users, as well as the high-level tasks that they were asked to perform, including rating the explanations of a single approach and comparing explanations of multiple techniques. Generally speaking, human evaluation is a promising metric, but with very few use the well-established human evaluation method. And this is a clear gap in this field, and needs to be addressed in the near future. Although there were very few well-established human evaluation strategies, we indeed notice one human evaluation method that worth mentioning. It is called the trust evaluation method used in the work done by Sidorova et al. They borrowed the idea originally proposed by Silvaraju et al. In 2016 for evaluating their computer vision models. The main idea of which is the following. Given two models with different performances, instances are chosen that are classified correctly by both models. Human annotators are presented the predicted instance of together with their explanations generated by the two approaches, and the humans needed to rate the reliability of the explanations without knowing which explanation is produced by which approach. The main point is that since it considers only instances that the two approaches agree on, the reliability score is purely determined by the explanation. Effective explanations should help humans identify the better approach. Here's a screenshot of the interface they used for human evaluation. As you can see, the interface shows the explanations generated by two different models in left and right, but which model produced which explanation is not shown to the user. And explanations of a particular model may appear in the left or right of the user feedback interface randomly, so that the user can rate the explanation based on solely their effectiveness without being affected by the provenance info of the explanation. Trust evaluation has been widely adopted in computer vision domain, but not frequently used in NLP domain. We think this is a good example of using a well-established evaluation metric. One of the nice properties is that it's a model agnostic approach, indicating that it can be applied to different NLP tasks. However, we have seen very few such strategies from our literature review, which is another major gaps we have identified for our research community to address in the near future. Apart from evaluation metric, another important and often overlooked aspect for evaluating the quality of explanation is that which part of the prediction process, starting with the input and ending with the model output, is covered by an explanation. We have observed that many explainability approaches explain only part of this process, leaving it up to the end user to fill in the gaps. Take MathQA as an example. MathQA tries to solve the problem that given a math question expressed in natural language, derive the sequence of mathematical operations or programs to get the final answer. For example, if the math problem expression is how long does a train 110 meters long running at the speed of 72 kilometers per hour takes to cross a bridge 132 meters length. Amelia et al. Designed a model using declarative induction explainability to derive a sequence of mathematical operations or programs such as at 110 and 132, multiply 72 by a constant 0.2778, then divide the first number by the second number, then use floor operations to get an integer number. At first glance, the generated explanation can be understood very well by the user. However, if we look deeper at their method, the way that they generate the sequence of mathematical operations is by using a classic encoder-decoder model, which involves a deep neural network with a lot of layers between the input words and the output mathematical operations. This chart illustrates the architecture of their model, as we can see that they actually have an intention layer between encoder and decoder, which enable the feature importance explainability, but the author chose not to use salience heat map to show the input-output alignment. We are not trying to say that salience heat maps are much better, because they cannot give very detailed information about the reasoning logic behind the decoding part, but without it may cause some confusion in the math QA cases. When we discussed this paper during our literature review, many researchers found it very mysterious how the model came up with the mathematical operations. It was a black box to the user. On the other hand, if the author also provides the salience heat maps that visualize the input-output alignment along with the derived mathematical operations, it will give some insights on how each individual mathematical operation was derived from the original question expressions. Therefore, we think this is a good example to discuss in this tutorial, that the generated explanations may not capture the whole predictive process, and sometimes it was caused by using a black box model to get the final predictions and the explanations, and sometimes it was caused by missing an important explainable part of the model, such as the MathQA model we show here, which has an attention layer, but the authors chose not to use it as part of their explanation. Fidelity is another important aspect when we design an XAI approach. Fidelity is actually an issue arises in surrogate model-based approaches. We all know that surrogate model is flexible since it's model agnostic. Prior surrogate model-based approaches such as Line focuses on the local fidelity and the global fidelity issue. There's another important aspect, which is the logic fidelity issue. As we said earlier, a surrogate model-based approach is very flexible, but the flexibility comes at a price. That is, the proxy model may have completely different mechanism for making predictions. For example, you can use a linear model to explain a deep learning model as long as the linear model is locally faithful to the deep learning model in the line-based approach. However, we may ask the question that is it really wise to use a linear model to explain a deep learning model? Can you really trust the explanation generated by a much simpler model? These kind of questions are very important, especially when we try to apply so-called XAI approaches in real-world scenarios. And this type of question have been less studied in the past.
Hello everyone, my name is Shipi Dhanorkar and I'll be covering the third part of our tutorial. As the explainability literature points, a very few percentage of papers had some form of human evaluation of the explanations that AI models generate. As contemporary AI products become sophisticated, so do their complexities. People with different backgrounds and expertise might be interacting with the AI model. Simultaneously, the growing realization of the substantial roles that the AI models play as arbiters of human lives brings explainability to center stage. The design space for explainable AI, therefore, is inherently human centered. The human computer interaction research area is burgeoning with research on AI explainability, especially one that brings a sharp focus onto the user or the human perspective. Scholars have synthesized guidelines for human AI interaction that touch upon some aspects of explainability, like making clear what the system can do, how well it can do it, and why it did what it did. Explanation has long been studied in different fields such as cognitive psychology, communication, and even more broadly in social sciences. Miller's work summarizes some of the facets of human explanations. First, explanations are contrastive, they're selective. Third, they have flavors of causal language, and they're socially constructed. Researchers Wang and colleagues have argued that the design of explainable AI can find inspiration in human reasoning to approximately map explainability techniques with cognitive patterns. Such an intentional mapping can drive synthesis between AI and humans. The work of Wolf acknowledges the need to bridge the gap between AI algorithms and their explanations by examining actual settings of end use. Recent work also points to the need of applying a wider aperture in understanding AI explainability, one that considers the broader ecosystem of actors who hold a stake in the AI system and who are keen to understand how it works and what effect it will have. So now we turn to the third part of the tutorial. This part is really exciting because this is the part where we see a nexus between models and humans. In the first part, we introduced and motivated explainability with examples. In the second part of the tutorial, we provided an in-depth review of the literature with all the groundbreaking work in explainability techniques and visualizations. In this part of the tutorial, we dive into how explainability manifests in real-world projects. Little is known about how AI researchers and practitioners enact explainability in industrial settings, what forms it assumes, and the tensions that concurrently simmer in its implementation. Our work is motivated by the desire to better understand the range of stakeholders involved in seeking and giving explanations about AI models, when they become involved, and how their explainability needs, along with the derived explanations, emerge in situated encounters with the AI. These concerns motivate our research questions. First, what is the nature of explainability concerns in industrial AI projects? And second, over the course of a model's pipeline, when do explanation needs arise? To capture a variety of experiences and perspectives across text analytics projects, we conducted an interview study where we recruited broadly and required each informant to have worked on a text project in some capacity and to have explained to another person how AI explanations for text work. These explanations could have been delivered internally to project team members or externally to clients. Accordingly, our informants represent a range of roles across a variety of industrial AI projects, including technical development roles like data scientists and AI engineers, those who are in strategic development like technical strategists and product managers, as well as those focused on user experience and design. Our informants represent a range of AI expertise, some who are relatively newcomers to the world of AI. One product manager talked of the brutal steep learning curve to get himself acquainted with AI on the one hand, and several years of experience or grad level expertise on the other hand. In this study, we only targeted individual employees. Follow up work on this could certainly include interviews with AI end users or clients. In this study, their enrollment was practically constrained by their access given the proprietary nature of R&D projects. We also encountered a variety of business domains and problems motivating AI model development in the first place. For example, document analysis in business communications like emails or legal contracts, identifying key opinion leaders in the medical domain, text generation for HR applications, conversational quality monitoring for chatbots, and so on. Many of these use cases can be organized into two high-level motivations: augmenting existing business workflows and then discovering of other new insights. We followed a semi structured interview approach that allowed informants to guide the discussion and contribute to an interactive exploration of our inquiry areas, namely who touches the AI model, what are their informational needs, and when do explanations get warranted. Our participants offered us tremendous insights that were really very useful. During the interviews, many informants also showed us artifacts that they had developed to explain models or use themselves, like slide decks, dashboards, visualization applications, and even scientific papers. All interviews were audio recorded and transcribed, and we also took notes during these interviews. We iteratively analyzed the interview transcripts and notes, beginning with open coding, to develop categories and themes. AI models do not exist in a social vacuum. AI models sit at different points within a socio-technical system, and a model's location shapes the type of explanations that are needed and for whom. As described by our informants, discussions about AI model technicalities take place amongst individuals with different backgrounds. A technical strategist remarked, not all AI models are end to end. Some are directly human facing, and some are embedded in the enterprise pipeline. Depending on where they sit in, there could be different personas that interact with these AI models. This is an attempt to represent stakeholders of explanations throughout the AI lifecycle. And we acknowledge that other organizations might have personnel with more specific or slightly different roles at each stages. Nonetheless, the juxtaposition of our findings from the field about the form and function of explainability with the AI lifecycle is notably illuminating. We found particular notions of AI model explanations. Example, those that are about how the model is built, why an output is manifested the way it is, appearing throughout the AI pipeline, and the related AI product service within which the model was embedded. We abstract ourselves a bit from this fine-grained life cycle stages and focus on initial model building, proof of concept stage, and model introduction. The initial stage of model building entails rapid iterations and exploration to develop technical assets that serve as base models. Early in the AI pipeline, model trainers primarily seek explanations to obtain a sense of why a model is predicting what it is and what linguistic features it might have learned. One data scientist who also works on information visualization noted, explanations can be useful to NLP researchers explore and come up with hypotheses about why their models are working well. He continued to elaborate the use of explanations to gain an understanding of BERT's inner working. This informant demoed a visual tool that he had developed to explain BERT. In his words, if you know the layer and the head, then you have all the information you need to remove its influence. By looking, you could say, oh, this head and this layer is only causing adverse effects. Kill it and retrain, or you could tweak it perhaps in such a way to minimize bias. Similarly, other details like hyperparameter tuning can be informed by explanations and could also be used to debug or brainstorm different algorithmic designs. A data scientist mentioned that during conceptualization and initial model development cycles, explanations could come in very handy in selecting the right model. Explanations give model trainers and developers a useful glimpse into particularities, allowing the best one to be chosen for further validation. An important part of discussions with client revolves around data, and this was a dominant theme throughout our informants accounts. Discovery motivated AI product offerings might involve incorporating novel sources of data, like social media data, into an existing business process, which in turn requires explanatory work. For example, a data scientist working with professors and doctors in a medical school on analyzing clinical documents indicated domain experts want to know more about the public medical data set that the model is trained on to gauge if it can adapt well to their proprietary data. One product manager described how explanations during proof of concept stages are accompanied by a nuanced set of model explanation seekers, like model validators. For example, in the financial domain, they could be risk management personnel who are familiar with regulatory requirements and policies. However, he mentioned that individuals with different background could be interacting with the AI tooling. He described, initially we had a machine learning operations kind of persona in the client data science team, who is supposed to be relatively up to speed in what is involved in the caring and feeding of an AI model. However, subsequent engagement with the same client lacked personnel with such a definitive job title, he recounted. The responsibility for the model later fell on the IT operations team personnel who had limited experience with AI models. Bringing an AI based product or service to life is a joint process between domain experts and model developers. Information sharing across a domain and model development undergirds this joint process. Subject matter experts describe to model developers the technicalities of their domain, while the onus of explaining the model's functioning and its behavior to the experts falls on the model developers. Our informants emphasize the shifting focus in the explanations that they offered. I4, for example, described, initially, we presented everything in the typical AI way. That is, we showed the diagram of the model. We even put equations, but realized this will not work. After a few weeks, we started to show only examples and describe how the model works at a high level with these examples. During the initial model development phase, clients and their legal teams provide high-level privacy requirements specific to their domain. These requirements feed into the data pre-processing steps, during which model developers generate masks and filters for personal data. Our informants discussed transparent and open have discussed openly and transparently about this data preparation and the conceived mapping between privacy and security requirements, the data masks and filters that occur during the proof of concept stage. Here, clients raise questions pertinent to regulatory issues with respect to the AI model. Explanations are geared to assure legal compliance. One product manager recalled a client asking, "How do we know the model is safe to use?" Users will ask questions about regulatory or compliance related factors. Does the model identify this particular part of the GDPR law? Explanations, conceivably so, are also warranted when a model's behavior in production needs to be understood. Our informants' accounts are captured in two different themes: expectation mismatch and the role of explanations in providing clients with actionable insights. An HCI researcher aptly characterized expectation mismatch between the model predictions and any given user's anticipated prediction from the model that necessarily elevates the need for explanations. In the context of a client problem statement of coming up with a list of top 100% recommendations in a particular type of cancer research in the European Union, one of the technical strategists described an AI service that uses entity resolution. The informant described the service as one that augments the current manual process of creating this list of key opinion leaders. Customers seek explanation when some names they expect to see on the list are not captured by the AI model. Referring to an erroneous name consolidation process, the technical strategist explained, data quality issues might arise resulting from expectation mismatch, but the list of recommendations must at least be as good as the manual process. If the clients come back with data quality issues, we need to provide an explanation of what happened. Another technical strategist indicated that explanations help in distinguishing between outputs manifested through model mistakes versus decision disagreements. In our conversation with our informants, we saw explanations as closely intertwined with business actionability. Explanations ultimately propel a model's meaningful integration into business workflows. Therefore, it is crucial for explanations to accommodate the constraints of the broader workflow or business domain within which they are provided. One data scientist, I-22, used the language of mutable and immutable variables to describe this concept. She brought up questions that clients often ask her. Is the feature it is pointing to something I can change in my business? If not, how does knowing that help me? We have walked through in detail about the different ways model explanations are sought and offered. We capture these findings in a visual representation here with the three high-level areas of model building, model validation during proof of concept, and model in production. We include the primary audience and their explanation needs throughout the AI model's lifecycle. To recap, the initial model development phase relies heavily on explanations to peek inside AI models to understand their inner working, improve their designs, and ultimately select the ideal-most one for further stages. Proof of concept demonstrations rely heavily on communication about the data on which the model was trained, understanding high-level mechanics of the AI model, and ensuring its design meets ethical and regulatory standards. When the model is in production, explainability is triggered when expectations are violated. Furthermore, for using AI models in their main workflow, business stakeholders need assurance that explanations they generate can prompt business actionability. Next, we take the case of Heidel, covered previously in part 2, to examine how explainability is an integral part of its design. We introduced Heidel, a tool that helps build an in-depth understanding of legal contract documents by automatically labeling sentences into contractual clauses like communication, termination, or payment. Explainability takes on two dimensions here. First, the rules that are generated are based on semantic linguistic structure and hence are much easier to understand as compared to those based on lower level syntactic features. Second, even though the initial set of learned rules are generated by a black box and there could be hundreds of them, Heidel allows users to interactively explore them in relation to their component parts and metrics. Subject matter experts can infuse their domain knowledge by individually examining each rule and further approving or disapproving them based on their metrics. They can also control which component predicates get added or dropped. Through this mechanism, users are offered higher agency over the rules that ultimately impacts the labeling of the contract document, thus offering a platform to engage in a joint co-creation process. Another affordance built into Heidel is immediate performance feedback resulting from the user-driven changes. Whenever users interact with a system, they need to know the impact of the interaction or change. Being able to quickly see how performance changes on refining rules or even accepting or removing them completely offers a glimpse into the working of the model. This improved visibility, in a sense, promotes explainability.
Hello everyone. In the next, I will talk about design implications based on our studies. First, in the design process, we need to consider the gaps between stakeholders' information needs and their AI knowledge. So basically, we find that many stakeholder owners, they do have significant amount of information needs about these AI outcomes, but sometimes they have very limited machine learning background. So this is definitely a challenge we need to consider in the design process. Second one is in our study, we find that in this team, in this collaboration environment, there are different kinds of users. For example, it's a mixed. One team is a mix of data scientists and product managers. When members have so much diverse background, um, it's sometimes it's difficult to design this information flow among different types of users. So in the design process, we need to consider how can we design a group collaboration persona to actually capture all these distinct type of members in this process to explain AI. The third point we want to make is, again, since we have different kinds of users, their learning curve can be very different. So in our study, for example, we find out if we wanted to approach end users, the learning curve should be very shallow. So this actually further limit our design space. So definitely we need to consider that there's a trade-off between simplicity versus complexity. Finally, in our study, we found that surprisingly, privacy could be a concern when we explain models. Participants report that when we explain AIs, some of these features can reveal, say, information about their employees and the department. So in the design process, we definitely need to consider that. In the future work, at high level, from human-computer interaction perspective, we should emphasize this user-centered design of AI explainability. So far, you can see in this work, what we have done so far is we conduct qualitative studies about user needs, and we actually studied different kinds of users, including business users, product managers, AI engineers, and data scientists. In the next, we wanted to bring end users into this picture, and more importantly, I want to emphasize this measure part. Very few work has actually studied users' perceptions of AI explainability. We don't have a comprehensive way to actually measure, or you can say quantify, users' perceptions of this AI explainability. So future research should definitely emphasize that how can we better measure the outcome of AI explainabilities from user perspective. Once we can better measure that, we have a way to better improve that. Finally, in this work, we studied this AI life cycle at a very high level. So it only have 3 steps from this model development, proof of concept, and model in production. But in practice, we do know that this AI life cycle can be much fine-grained level. In the future research, we should zoom into these individual steps to better capture users' needs. And to sum up, we do think there are a lot of good opportunities to better explain AI from a human-computer interaction perspective. And we do believe we should have this user-centered design approach to better explain AI. Thanks.
I believe all of us agree that AI has become an important part of our daily lives, and therefore, explainability is becoming increasingly important. It is an emerging research topic in academia and also an important requirement for many real-world AI applications. At the same time, we need to realize that explainability for NLP is still at its early stage, and there are many gaps and the limitations needs to be addressed. It is not surprising that this field lacks standardized terminology, given that it is still at the early stage. Having a unified terminology is very important for this field. When people talk about different concepts using the same term, or when people use the same term but actually mean different concepts, it will cause a lot of confusions and really hinder the development of the field. We made an attempt to define the terminology that we think they are appropriate, but we need help from the whole community. This is actually not just a challenge, it is a requirement for the whole community. The second challenge is that when designing explainable AI solutions, many people have the stereotype that we have to sacrifice accuracy for explainability. For example, we observe that a lot of work chose to first learn a complicated black box model, such as deep neural net, and then use surrogate model to provide explanations. However, as we discussed in the second part of this tutorial, surrogate model suffers logic fidelity issue. That is, oftentimes, it either uses a much simpler model to explain the prediction made by a much complex model, or the surrogate model uses a completely different reasoning logic to make the predictions. In this case, can you really trust the explanation generated by a surrogate model? The reality is that, in spite of that, people still use a surrogate model because they have the stereotype that we have to sacrifice accuracy for explainability and not willing to design self-explaining methods. Our argument is that it is not true. As argued by the Book of Why, the question of why, the cause and effect, can never be answered by data alone. In order to build models that are both highly accurate and highly explainable, we need to rethink new ways to fuse learning and reasoning. With the advances of the explainability research, there are many promising ways to directly produce self-explaining models that achieve near state-of-the-art or state-of-the-art results. We mentioned a few in the second part, such as some explainability-aware architecture design, and there are also some new ideas such as neuro-symbolic AI. We hope there will be more research on this direction in the future. The third challenge is that explainability needs to take into account different stakeholders. We have shown this chart in part 3. We would like to show it again, emphasizing that the explanation is stakeholder-oriented. Different stakeholders have different expectations for the explanations and the different skills and knowledge to consume explanations. Knowing the target stakeholders beforehand so as to appropriately design the explainable model is very important for the overall success of the whole explainability solution. To be specific, let's consider a concrete example. Here we need to provide explanation for a classification task in legal domain. Assume that we have two stakeholders, an AI engineer and a legal professional who doesn't know computer science. When providing explanation for the reason that why the highlighted sentence has labeled risky, for AI engineers who has been trained to understand the technical language such as the rule shown here, he will probably be happy about the way that the explanation is presented, which gives him all the information to understand the result and possibly debug the algorithm. However, the same presentation of the explanation may not make sense to the legal professionals, who probably can understand the rule or may expect more detailed information, such as the explanations in the second call-out balloon. From our literature review, none of the papers considers different stakeholders, and this is clearly a gap, but also an opportunity for future work. The next challenge is that we need more well-established evaluation methodology and metrics for explainability evaluation. In the second part, we mentioned that most of the papers we identified do not have any formal evaluation, which is clearly a gap. We talked about the trust evaluation, an idea borrowed from computer vision, and it is a well-established evaluation methodology. But that's not enough. We need more evaluation methodologies that ideally takes into account different types of stakeholders. In addition to evaluating the intuitiveness and the quality of generated explanations, we also need a metrics that measure two other important aspects, that is coverage of the prediction and the fidelity, as we discussed in the second part of the tutorial. Again, both the new methodologies and the metrics should take into account different stakeholders. Before we complete the tutorial, our last comment is that explainability research for NLP is an interdisciplinary topic that is at the intersection of computational linguistics, machine learning, and human-computer interaction. Here we quote two comments from the reviews that we received when we proposed this tutorial. One reviewer said that this tutorial is on a hot area in NLP and takes an innovative approach by weaving in not just core technique research but also user-oriented research. And the other reviewer said that I really appreciate the range of perspectives, social science, CI, and NLP, represented among the presenters of this tutorial. We can clearly see that NLP people really appreciate the idea of bringing NLP and the HCI people together, and we believe the NLP community and the HCI community can work closer together in the future to get the low-hanging fruit. To close our tutorial, we would like to thank you for staying with us for this 3.5-hour journey and your valuable comments and feedback. We would like to let you know that we have a survey paper to be presented at ACCL 2020, and the session information is listed here. We welcome you to attend that session. Finally, a few words about our team. We are an NLP research team at IBM Research Almaden. Our work focuses on NLP, database, machine learning, explainable AI, HCI, and etc. If you are interested in our work or are interested in future collaborations, please visit our website or simply drop us an email. Thank you again for attending our tutorial.